Welcome to our February Sacramento Symphony meeting. Thanks for joining us. I'm Bob Huddleston. I'd like to just introduce our Sacramento Symphony board quickly. Our chair, Paul Turner. Secretary Treasurer Mona Smother.
Somebody needs to mute.
Is here tonight. Myself, Tim Walker, John Hinkle, Robert Erickson, and John Malone. And, I want to thank those people for volunteering their time and helping us with the section. Just a couple of things I wanted to go over regarding Symphony membership. Being a member, there's all sorts of benefits for you, including the motion imaging journal about monthly, live webcasts, virtual courses, blog, Newswatch, Insights newsletter. We just mentioned it because potentially you're a member and are aware that there are some nice benefits for you. Also, if you're not a member, I encourage you to join. There's actually 6 membership levels. And also Simply just introduced new pricing model where you can actually pay by the month rather than annually. So just want to let you know about that. And just really quickly, just to walk down some of the benefits that are available. This is the membership benefits for the early career level, which includes access to SMPTE standards, subscription to the Motion Imaging Journal, full access to self-study virtual course library, a discount on conferences, subscription to newsletters, access to webcasts, networking opportunities such as we're having here today. So just a lot of great benefits. If you're not a member, I encourage you to join SMPTE. And then bring up Matt, who's going to introduce our speaker for tonight. Bob? Yeah.
All right. Tonight is my pleasure to introduce you to Ronny van Belle, who is our technology manager for our image processing central group in Belgium. A little bit about Ronny. He obtained master's degrees in both electrical engineering and mathematics and joined Barco in the mid-90s. As an electronics design engineer, he's worked on almost every product line that Barco does over the years, from projection to LCD to various medical displays and network video transport systems. Through the years, he's continued to innovate on real-time image processing algorithms suitable for newly introduced display technologies such as DMB chips. They're used in cinema and rental and staging markets, LED walls like this. And we can attest this has got a lot of his stuff in it right now that we're looking at. LCD-based monitors, and for healthcare, broadcast, post-production, air traffic, and defense. Today, Barco is still active in most of those markets mentioned. Dedicated R&D teams creating products in those markets all around the world. Since 2010, Ronny's been part of our central technology office, where until today, he's leading the corporate image processing team, which also includes Michel, who's here with us from Belgium today as well. They work on new technologies required for demanding applications in Barco's markets and market-leading products worldwide. Low latency image processing solutions created and supported by his team are supported by 85 patents, applications, and cover domains such as motion, performance, display calibration, and video format conversions. And with that, we will switch over. Ronny.
So the scope of the meeting of today is about high dynamic range and what it really means to mainly to display technologies. So how it impacts us and what it means from a designer's perspective, from an image processing perspective, how it complicates certain things. So, but before I can dive into some of the details, I'm not sure if everyone is familiar with some of the basics of the human visual perception. So I will spend a few slides on 2 basic properties of the human eye. Then I will discuss a bit what makes HDR standards and HDR processing different from handling SDR. It's more than just the H So the number of the dynamic range, there's more to it. And I will also discuss some of our latest HDR technologies, display technologies we have introduced and we will be introducing even this year. We also live in a world where you have a mix of many different dynamic ranges in multiple systems. So there's often the need for dynamic range tone mapping. I will discuss a number of the applications we see in our systems. I think they are representative for a huge number of other applications as well. And then I will dive into some of the implementation techniques for performing this dynamic range tone mapping. I will discuss a bit about the color gamut mapping that is required for handling different types of color gamuts and how this complicates a number of things from the display perspective and for the image processing itself. And then I will discuss the final step of a typical HDR image processing chain, which is decoding. Decoding is required in HDR systems, where it is optional in SDR video. You cannot see this as an option any longer in HDR. But first I need to start with a little word of a disclaimer. Marco, you have all seen the first slide, so it's the very nice building that's actually located in West Flanders. And you have to realize that in West Flanders, there are, that part of Belgium, we have 12 high-tech companies, but we have 183 breweries. And on the other hand, the other pie chart represents the amount of human citizens versus the number of pigs in our region. So we tend to base our wisdom a lot on referring to pigs and beers. So if that's, let's say, coincidentally slips into my presentation, you'll be surprised about it. Despite the fact that we're located there, we managed to build up quite a nice patent portfolio. I believe we have 85 quite strong patents in quite a few differentiating features, such as the motion performance of our display, like display calibration, which includes quite specific algorithms towards handling HDR signals, and also on video format conversions like scaling, interlacing.
This is Miniat Fanatics, and I hope you're all having a wonderful day.
Hope that was not a question because I did not understand. So we did also here on video format conversions, that includes topics like dynamic range tone mapping, where we did a lot of research on how to maintain the perception of colors when performing tone mapping. So let's start with some basics on the human visual perception. And first starts by referring to the year our current colorimetric system it was invented, let's say, or characterized. That was done by the Commission Internationale d'Éclairage. That was done in 1931, and these images give you an impression how old that is. So that colorimetric system is based on characterization of the three types of receptors we have in our human eyes, and it leads to a three-dimensional response to three stimuli. We call, not very originally, X, Y, and Z. So X, Y, Z defines, let's say, the perception of a spectrum for the human eye, which means that a full light spectrum only has three parameters, which means that you can have two very different light spectra and still have the same color perception. The reason why I'm mentioning this is because this at that time in 1931, they did not have a lot of, let's say, modern light sources like monochromatic laser light and LEDs. So they had nothing anywhere near this kind of spectra to characterize. And this is one of the reasons why there's a lot of need for perceptual matching. Why in color matching applications, you typically have to deal with either colorimetric matching, where you need to prove that colors are okay, and you can accurately prove that the colors are fine. But then you switch to perceptual mode, where the human eye sees the right colors. And this is especially applicable on, for instance, technology like this, LED bulbs, and on laser projectors, for instance. So this is a bit of the background. So let's remember there are 3 stimuli, and these 3 stimuli lead to another type of representation. You can rewrite these 3 stimuli, referred to as the large X, capital X, Y, Z. You can rewrite this as a 2-dimensional chromaticity and luminosity. And if you isolate this 2-dimensional chromaticity, then you have probably all seen this type of color representation. So the important thing you need to remember here is if you define 2 sets of primaries, for instance, in this case, there are 2 color spaces mentioned, XY, XPYCC, which is a white gamut in the standard HD TV, Rec 709. You can use the 2 sets of primaries to mix any color somewhere inside these 2 triangles, and they will be perceived as the same color. So one thing to remember is that color mixing is really linear in amount of photons. So if you mix this color with that color, let's say 50% of both in amount of photons, then the eye will see a color here in between. So color perception is quite linear. That doesn't mean that all steps in here are perceptually the same for the human eye. You can convert these formats, of course, to other more perceptual models. I don't go into too much details about different representations like LAB or L star, U star, V star, and so on. But do remember that color mixing is linear. It will be one of the reasons why processing HDR sources is quite difficult, or it can be a challenge. The other property, fundamental property, is the non-linearity or the non-linear response of the human eye to luminosities. And I took a very simple definition of that. So the response of the human eye is depends also on the use case and on ambient conditions. One of the standards that arises throughout the years is DICOM. And DICOM is the simplest perceptual standard you can imagine. You have a very dark room. You illuminate a small circle of white light, like 2 degrees, and you let an observer mark when he or she sees the difference, and then you note one just noticeable difference. You do that again and again and again. Every time you see the difference, you just mark the levels. So you have a transfer function from between just noticeable difference and the amount of light. And this is, let's say, a typical example of how light is perceptually encoded. In fact, all video standards tend to perform a kind of approximation for a specific set of use cases, and that includes like sRGB, Rec 709, XPYCC, hybrid log gamma, and including Dolby PQ and so on. So most so-called electro-optical transfer functions tend to approximate the linear quantizing of or try to perform linear quantizing perceptually for the human eye, for a specific use case. So if we go to in a bit more detail about what makes a difference, high dynamic range display in some Some papers will refer to high dynamic range just as the contrast ratio, the ratio between the white level and the black level. And if that's large enough that you have HDR display. If it would be as simple as that, then every barcode LED wall or every LED wall on the planet would be in high dynamic range display. And this is obviously not true. Try to put HDR content on a standard LED wall not prepared for it, and it really looks awful. So there's more to it, and you need to take into account the smallest step which is perceivable by the human eye. So this is the darkest, so it's the ratio between the biggest modulation you can obtain. So that's the difference between white and the black level, and the smallest modulation you can apply, which is noticeable by the human eye, which is the darkest gray level minus the black level. And if this relation is high enough, then you can speak about an HDR display. There are different variants of this definition, but I will stick to this. High dynamic range means that this ratio must be larger than 64K, in fact. And it also means that the contrast ratio must be larger than that. For instance, for the mastering display, for instance, the recommendation of Dolby is to have a contrast ratio even higher than 200,000. But that doesn't tell anything about this, because it would turn a LED wall also into a mastering display, and you don't have enough precision with the standard LED wall. So with our Infinipix-driven LED walls, you can really have HDR response. There we can have a dynamic range of 16 million, in fact. So the second thing, which the first thing is quite clear, but the second thing which distinguishes HDR processing and HDR sources from SDR is that with in a full SDR processing chain, you capture the real world, you apply a camera or whatever is the capturing device, will apply an optoelectrical transfer function. As said, this is done because it uses the bits better on the link, so it's actually a way of perceptual encoding. So this transfer function optimizes the bitrate on the cable, basically. Then you do the opposite function and you apply it to a linearized display. So this is happening, let's say, in an ideal display. So coincidentally, I took Barco's reference display as an example here. So what you see is that the relation between the photons you see here and the photons of the real world acts like neutrally colored sunglasses. It's really a linear relation between the two. Most of the time, the real world is a lot brighter than the display, so it's really acting like just an attenuator. That's the relation between the two. With HDR standards, it's a bit different. The chain is pretty much the same until here, but HDR standards, they come with an optical transfer function, or sometimes also electrical transfer function, but they perform what is called a rendering intent in between the two images, the image on the display and the image on the world. So HDR deals with what happens is if your display is much brighter or much darker. And this is something completely ignored by SDR standards. So as an example, I took one of the recommendations, the rendering intent recommendation of the Rec 2100s, where the output is supposed to be a gamma function. The amount of luminosity is a gammatized function of the input. You can read the formula here. That means that there is one variable here, and this is the amount of light coming out of the display. So it's the display level or the brightness of the display. So the brighter the display, the higher this gammatization function will be. So it's like a curved function. So if you put the hybrid low gamma signals on a very bright LED wall, you need to kind of gammutize the signal more than when you put it on a standard on a screen like this, for instance. So this is quite different because the HDR standards recommend this, and this comes with also a lot of the consequences, of course, when you perform image processing. So let's discuss a few of the HDR technologies. This one is rather new. So Barco has just announced this one publicly, and yeah, we will hopefully sell a lot of those by this year. So it's the final phase. So this is a light steering with projection systems. What is special here is that you use a type of phase modulator to steer the light only where it is needed. So conventional projector illuminates the full, whatever display technology is used, like a DLP, for instance, DLP chip, it is fully illuminated. If you want black color, you just rotate the mirrors and something blackish comes out, but the contrast is quite limited. So typical DLP-based projectors have contrasts in the ratio of like 2,200, something like that. So what we do with light steering, we start from a laser source. This is important because it must be a correlated light bundle. There is a beam expander, kind of duplicating the laser beam, because otherwise you cannot illuminate the full panel here. This folding mirror is here just to save space and to make it in a compact space. Otherwise we would make a projector like 2 meters long or so. It will not be a big success. Actually, it is almost 2 meters long. It would be 4 meters long. But then there's a special part here, that's the phase modulator. So all displays actually allow the light to go through the display. In this case, it's a reflective display, so the light goes through a bit, then returns. And so there's an optical path length there. And by modulating the signal, this panel actually doesn't know it is a phase modulator. You're just using it like that. So you're modulating the phase, you're removing all polarizers from it, and that's what normal displays do. When you remove the polarizers, it's on an ALCOS display, it acts like a phase modulator. And so a phase modulator, you have to think about this as a lens. We all know the shape of, let's say, a typical lens. If light goes through, the light converges because of the different optical path lengths. And this is what's happening here. So the different optical path lengths that translates into different phases of the light. And so we can steer the light towards certain areas on the panel, which means that actually you have 2 modulators, one after the other. And so you can increase the dynamic range of the display a lot by doing that. So you actually have 2 sequential modulators here. And so by nature, you preserve the full accuracy of this modulator, regardless of the light intensity you put here. So for a given dynamic range of the system, like 2000, for instance, you can completely preserve this for every single light level. That's how it's working. So that means you automatically get the same precision in very bright areas compared to very dark areas. And this is one of the big advantages of this technology. It allows you automatically to have very fine gradations of luminosity in dark levels. And this is what making this, by nature, let's say, a very good high dynamic range technology. Here you can see what's happening to the dynamic range of a typical projector covering the DCI spec. With light steering, we can go at least 5 times lower in the darkest levels and more than 10 times higher in the simultaneously. We can do that, so we can go 10 times higher in the highlights. So that results in a much higher dynamic range. And so that results in very fine color details also in the dark levels. Of course, we are from West Flanders again. I want to mention that, you have a lot of precision in the dark tones, but one of the challenges in the bright lights, you don't gain precision with the system because the modulator doesn't help you gaining precision in the bright tones. It helps you to gain the precision because it's a multiplication. Both are equally, let's say, precise. It doesn't help you to add precision in the bright lights. And one of the most challenging things, at least we are aware of in Belgium, of course, it's about beers. So during the movie, people always say in digital cinema, skin tones are very critical, but that's totally untrue, at least in Belgium, because you see people of all kinds of colors anyway. And but if there's advertising about beers, this is very, very critical. And this is true. I'm not making this up. The salesperson of the brewery of Duvel came to Barco explaining that this beer looked too much like another beer, very local to Barco. So there's a brewery about two miles from Barco. And the color of the beer was slightly off, he thought at least. So we had to add some perceptual matching algorithms to really make the color of the beer appear correctly. I'm not making this up. Again. So another technology which does not gain from this dual modulator principle is LED wall. An LED wall by nature, you can say, okay, these are LEDs, light emitting diodes. You apply a current and you get some light from it. It's driven analog, so it has an infinite precision. So what's your problem? Well, the problem is temperature drift. So if you would drive them in an analog fashion, it would not work. You can never make a stable display or a calibrated display. So that's why LED walls are driven by pulse width modulation schemes. So that means you have one calibrated current and you modulate that one calibrated current quickly in time. But because of the laws of physics, you cannot do that infinitely fast. So within a frame period, you get a finite precision. And that finite precision, in reality, somewhere stops at 14-bit, depending on the technology you're using and the cost you are prepared to put in there. So the problem is, this is not enough for handling true HDR. So how can you turn an LED wall with these physical limitations into an HDR display that can truly respond to every gradation in colors of, for instance, a hybrid low gamma signal or PQ signal? The way we do that is we use some adaptive modulation techniques. Basically, they average out neighboring pixels. So you simply cannot calibrate a LED wall per pixel with the same precision as HDR requires. But you can calibrate a very small region in a very, very short time and average that out. And with those kind of stochastic modulation techniques, we can have perceived precisions, even of the finest details, the finest perceivable details. We can have precisions equivalent to 24-bit, which is more than enough to handle any kind of HDR signals. So it might be a surprise that on LED walls, all people can see intensities even of 60 micronits. So remember, for the light steering, we were talking about, and for HDR digital cinema standards, we were talking about 5 millinits. Digital cinema starts there. HDR digital cinema starts there. On LED walls, you can see intensities almost 100 times lower than that. So this technology clearly has, in some cases, it has some advantages, like in virtual reality applications, where you can, for instance, in applications where you have interior car design, you're seeing the outside world, which is very bright, and you want to evaluate what is the effect of the dashboard giving a certain color. So this can be done with an LED wall. This cannot be done with light steering because the dynamic range is even much higher. So this requires really dedicated modulation techniques. I will come back on that further. But so this is one of the high dynamic range technologies. And the last example is, it's not very new, but we're also recently working on that. Put a Miniat array behind an LCD screen. The Miniat array, actually, it acts a bit like the light steering without all the physical trouble, because light steering is a lot more complicated technology than putting a LED array behind an LCD screen. So typical LCD screens are really limited to contrast ratios in practice up to 2000 to 1. Some can exceed that, but in reality, we see this type of contrast ratios. Of course, if you put a LED array behind the screen, you can dim locally, and you get virtually also infinite contrast ratios. So with a local dimming, you can receive contrast. And this has two types of applications mainly. In the surgical operating room, this helps to increase the highlights. So in a surgical operating room, I will come back on that later. There's a need to process HDR, even if the conditions are not there to view HDR. And in diagnostic display, it helps to reduce the black levels to see or to detect details in the dark tones in order to make better diagnosis. So these are a couple of examples of display technologies we have introduced or are introducing as we speak. Now I'll discuss a bit about the dynamic range tone mapping applications we have. First, I need to explain a bit what it really means. So the pictures you can see here show examples of what tone mapping can do. Note that it doesn't really impact the highlights. It doesn't really impact the darkest levels, but everything in between is highly non-linearly changed by the tone mapping algorithm. Internally, we refer to all this technology as Pac-Man. Coincidentally, it matches perceptual and colorimetric matching and normalizing. So as I said, perception and colorimetry does not always agree. That's why the two are there. You can switch between the two modes. Actually, you're not the only ones doing that. If you work with Adobe Photoshop, you can have perceptual rendering selected or colorimetric rendering, for instance, if you want to convert screen pictures to print them. So, and the normalizing means that, we always tend to use the full range of the display, of course. We take benefit of the full range, full capabilities of the display. So in barcode, this is one technology. This is where we are working on, Michiel and I. So it's one technology we made that can handle a number of use cases. And actually today we have implemented this technology, this tone mapping technology in 11 different product families. So let's take a few examples where we use this. So our first application is in control rooms. Control rooms that are equipped with LED walls. Often they have a mixture of HDR cameras, but also still have to deal with some SDR cameras. Now, if you put a standard SDR source like Rec 709 or sRGB, and you just display that on a LED wall without any processing, if that LED wall is like about 20 times as bright as your display you're looking at otherwise, then defects in the image are of course emphasized a lot. So especially colors simply look unnatural because the light is 20 times brighter and it is appearing a lot more vibrant. But also the noises can be very disturbing. So when mapping SDR sources to HDR displays, like our bright LED walls, we need to take into account some algorithms that can really benefit from this brighter image of the LED wall and the vibrant colors, but at the same time, the challenge is, of course, to preserve natural colors. So it's a bit of a contradiction. So people want to move from, let's say, a standard screen technology to a much more bright and vibrant LED wall, but everything must stay natural. So there is some processing going on to be able to guarantee that. So a second application is also on LED walls. The challenge is here is the opposite. If you have Dolby PQ as a source, for instance, it can contain content up to 10 K-nits. You might not want a display which goes up to 10 K-nits. If you put a LED wall in high-end residential application, you don't want a huge bunch of power supplies behind the screen to support peak output you almost never use of 10 K-nits. So even if you would want to put the cost in there, well, it's not ecologic, but it also does not enhance the visual comfort. If the peak brightness is too high for an LED wall, you get eye fatigueness, and so you're losing comfort. So if your LED wall is too bright, then you lose viewing comfort. If it's not bright enough, then you lose the vividness of the LED wall. So we found that the sweet spot is usually around 600 nits or so for this type of applications, 500 to 800, depending on the pixel pitch, the setup, and so on, ambient conditions. But that means you need to remap all colors up to 10K nits to something that stays within 600 nits. And so the challenge there is, of course, to recover all this highlighted detail, because it's such a very dramatic reduction of the dynamic range. You really need to do this in a dynamic way. And so one of the challenges is to perform the right type of temporal filtering so that it's not, let's say, changing suddenly within a certain scene. So you need to perform scene detection. You need to optimize your temporal filtering or proportional integral differential filtering, so that within the scene, the dynamics of it still stay natural. And so one of the things you can do, and to guarantee that certain colors or critical colors in your image stay natural, is use a bit of AI next to your image processing and let the AI tell you this is grass, this is skin tones, this is sky, and so on. Then you can optimize the parameters of your image processing in a dynamic way. So a third application is in the surgical operating room. This is actually one of the most interesting examples, because a surgical operating room does not have any HDR conditions at all. So you have a huge amount of ambient light. It must be very bright there, obviously, for the surgeon to function. On the other hand, when the surgeon is using an endoscopy camera, that endoscopy camera is within the patient. There it's usually a bit darker and it is illuminated in a very different way. And surgical tools tend to be quite reflective. And I was fortunate enough to try this myself. I did some surgery, not on a real human being, luckily not. It was on a paprika. Oh, I try to pull some pieces from the paprika using pincets and surgical tools. And by capturing HDR content in an HDR way and decently handling the HDR, I could see a lot of detail in the specular highlight reflections on the tools that otherwise are lost with SDR. And so the surprise to me was, I'm not a surgeon at all. I was like shaking my hands with SDR. When it was captured with HDR and the highlight details were preserved, my hand was suddenly more stable. Because I saw more details, my brains were processing that as, let's say, positional awareness. It's a form of positional awareness you have with these highlight reflections. And so if I feel that, then surgeons must feel that as well, of course. And so the use case for this, for capturing HDR, it's kind of a surprise. It simply makes the surgeon more, let's say, aware of what are the tools doing. And so eventually it will create a better outcome for the patient, or or I would say a more effective, productive procedure by the surgeon. So we need to dramatically remap the dynamic range of, for instance, hybrid log gamma, because it can contain content up to typically up to 1,000 nits. And the problem is that because of the ambient condition, you end up with a contrast even and a dynamic range even much below typical SDR conditions. So we need to perform a lot of processing in order to both visualize the shadows in the image, but at the same time also preserve the highlight details. And this is one of the most challenging types of tone mapping, because it's literally quite life critical. And we need to prove with clinical studies that this enhances indeed the patient outcome. Luckily, it is. And all this needs to be done at an extreme low latency. If you build up latency by adding this kind of advanced tone mapping, it doesn't work, because if the image is behind, then the surgeon would maybe cut a bit too far, and you really want to avoid it. At first sight, robotic surgery looks like, oh, this is just a similar example, but it is not. So it's quite different, because you can already see here, this is a doctor or a surgeon operating a surgical robot, but he's looking in a 3D display. And this 3D display is rather a controlled environment. It's not like it's illuminated by spots that are on the patient. So I'm capturing 3D content here together with the 3D obviously is also intended to have a better awareness of orientation and perspective. It clearly gives a sense of depth. So if you combine that with the HDR capturing, it kind of, those two techniques kind of magnify each other. So if you have 3D images and you capture them in HDR, it works even better, and you have a better awareness of it. So, and here this is really important, because the surgeon fully relies on the display naturally. And so the challenge here is, or one of the challenges, is that you need to process, if you're dealing with perceptual matching of both images, you need to ensure that the processing at both sides is matched in a way that it doesn't disturb the sense of depth that the surgeon sees. And of course, it's not necessary to mention that also here extreme low latency is required. And so the final application I want to talk about is in the event and entertainment market. If you walk through this building, you will recognize this thing. This building is worth a lot, but these things inside are even a lot more expensive than the building. So a lot of processing is going on, and one of the things we implement here is also HDR handling. HDR handling in these type of applications can be quite a challenge because you can have very extreme illuminations of a scene, for instance. Like you can see here, you have very local lights. It can be highly colored, so you might be very near to the color spectrum or the color gamut. So the challenge is, of course, to perform tone mapping in real time with a mixture of different cameras. There might be hybrid log cameras, but also some standard Rec 709 cameras. You might have a mixture of even wide gamuts and extended gamuts. I will come back on that later, what the difference is for those who don't know. And so the real challenge is to do all that with extreme low latency, perform all the fancy perceptual matching stuff with an extreme low latency. This means you need to really accelerate this in hardware. In this case, there are a few expensive FPGAs in there doing this kind of stuff. And so extreme low latency is required because you need to keep the video in sync with the audio. And of course, if you're a performer, you cannot really tolerate a lot of latency. It must be near zero. For those, I'm not sure if there are some guitar players in the room. If you play an electric guitar and you have like a 10-meter cable and your guitar amp is 10 meters away from you, your playing becomes really lousy. So I play the guitar. That's why I take this example. But I mean, if you're a performer, you care about latency. If you like musicians or other performers, latency is absolutely critical. So now that we have gone through a couple of the applications, I want to discuss some of the basics of the implementation techniques that you can do. So first, I don't want to dive into all possible implementation techniques that would lead us way too far, but I want to touch on a few basics of types of implementations we see. And I will discuss 4, let's say, levels of implementation you can think about. So first, quite obvious way to handle dynamic range and to perform rendering intents in either electrical or in optical domain is by just using a one-dimensional lookup table. You can also use real-time mathematical engines or DSP engines to perform similar functions, but they are not generic enough. They are hard to match with human visual perception, not tunable. So I will only discuss lookup table-based functions because that's what's happening in reality. So if you use this kind of technique for mapping, for instance, a PQ content mastered on a 4000 nits display, and you display that on a typical sRGB, like a screen of up to 300 nits. The problem is that while you can remap these highlights in this way, you're also desaturating colors a lot. If you would apply a skin tone through this circuit, for instance, you have 2 large stimuli, for instance, for red and green, somewhere over here, because it's yellowish, the skin tones. And there's, a little bit of blue, maybe, in here. Now, if you compress like this, that blue is not touched, but the other colors are compressed, which means this type of one-dimensional processing tends to desaturate images when you compress the dynamic range. So this is almost never desirable. Now, if you do the opposite with the one-dimensional lookup table, it can be desirable because then you're actually making colors more vibrant. The opposite happens. oversaturating the colors in your color spectrum. And for instance, this is not looking so bad if you perform this type of rendering intent on LED walls, for instance, because people expect quite crispy, vibrant images on an LED wall. So, of course, those results can be quite subjective. The real reason why this is often applied in many systems is that, yeah, it doesn't cost you anything, because whether it's an electrical transfer function or a pure optical rendering intent, it's you can simply combine that with your electro-optical transfer function. So if you have a lookup table and another lookup table, you can combine them in one. And so you don't need additional hardware acceleration. That's why you will find this a lot in many systems, but many systems that compress like this fail to show, let's say, saturated highlights. And you will see that in many of the effects created in HDR movies, where when compressed, this really desaturates the scene. So a way to overcome this is by using three-dimensional lookup tables. A three-dimensional lookup table allows you to really modify all the colors in the color cube independently, and you don't have to change the color if you change luminosity. Now, a problem with the 3D LUTs is that you are reducing, in practice, you're reducing the accuracy to perform some transfer functions, because you need to deal with the 3 dimensions. In 3 dimensions, you have many more anchor points to store in your lookup table. And so this is one of the limitations of 3D LUTs, obviously. In practical systems, they are limited in size. It is not implemented in not implementable in any device known in this universe, at least to me. To, for instance, implement a lookup table 1K by 1K by 1K to map every single video value to something else in real-time random addressable with 0 latency. So that's not implementable, and these methods, this tends to be used, this way of implementing the lookup table tend to be used with trilinear interpolation, which is quite easy to accelerate in GPU systems because it's a static form of interpolation. Unfortunately, this type of interpolation does not really, let's say, reflect the way the human eye perceives colors. So with problem is that within this XY diagram, what this figure represents are the so-called McAdam ellipses, and these represent equal differences to the human eye. So you can see that we're a lot more sensitive to differences near the blues than we are near the greens. So that means if you are using a 3D LUT, you must be doing quite some nonlinear functions in order to compensate for this mismatch in perception in that space. And so with trilinear interpolation, you tend to make a lot of color mistakes even near the gray levels. So that means this has some limited use. It can be very good for limited color rendering effects or even some calibration purposes. But if you want to dive a bit further, then you really need to perform 3-dimensional lookup tables with more advanced interpolation techniques. The problem with that is that if you go to interpolations that use, for instance, tetrahedrons, you need to adaptively process the points you're getting from the lookup table. And without diving into all these equations, summarized, I can say that you need to kind of branch the code into multiple cases, depending on where you are in the color space. Also, with that kind of circuitry, you can better approximate what's happening even for colors that are outside of the displayable color gamut. And so more advanced techniques use this interpolation technique based on tetrahedrons. You will find, if you're looking for some hardware boxes that can do that, you will see some companies offer solutions both accelerated on CPU or on GPU or on FPGA. And you will find the most advanced algorithms on FPGA. For instance, Filmlight Studios in London have these different options. So splitting the image in tetrahedrons, actually, when you looked up through the cube, through, let's say, the axis going through the white point and the black points, what you see is literally each tetrahedron covers a part of the XY chromaticity space. So the advantage of this technique in hardware that can be quite adaptive is that it even saves resources, because you only need to read only 4 points from the memory instead of 8 in order to perform your interpolation. But as said, this is not efficiently implementable on GPU-based system for the reasons that the code is branching. So the fourth and the final implementation example I want to discuss is the 3D LUT per subpixel. So you know that a lot of the displays have kind of subpixels arranged next to each other, like direct view LCD displays, for instance. They have this kind of arrangements where you, if you take magnifying glasses, you look at the screen, you will see red, green, blue, red, green, blue. So one of the problems with those displays is that if you turn on or you drive a red subpixel and you drive a green subpixel, you get a certain color. But if you drive them together, you're not getting the sum of the two. Why not? Because the electrical fields, they push away each other, like almost like magnets. You might remember when you were a child, you were playing with magnets, they can push away each other. So this is happening in this space. If you take the magnifying glass, you can see that actually on the screen of your laptop. So you see the optical apertures pushing away each other. So you see the two, almost like this, the two pixels are moving. So this is one reason why you need to compensate for this type of artifacts, and why the best thing you can do for applying 3D LUTs is apply that per subpixel, not per pixel. The second reason for that is, let's imagine you have a black screen and you put a white line on a black screen. This would be a white line, but this is also a white line. This also, from a distance, they are all perceived just as a white line because you have the three colors in there. So many sources render their anti-aliasing, for instance, like TrueType fonts. They perform anti-aliasing. Even if you look at the signal that comes out of your laptop, for instance, you will see that black text on a white background or vice versa is not uncolored. It uses this subpixel information because it knows the display is organized in this way. And so if the white line would be here or there, it doesn't make sense to compensate for this color and this color. So if you would have, for instance, a signal, if this would be a pixel and this would be a pixel, you can, if you combine those two subpixels, it will be a magenta line you will see, or a magenta detail. But if you use a 3D LUT per pixel, you're compensating for blue and for red. That doesn't make sense because the color you're observing from a distance will be magenta. So this is one of the most advanced implementations you can do. You need to do per subpixel processing. And per subpixel processing complicates things a bit. The good news is that in, let's say, FPGA-based implementations, it really doesn't matter because you have 3 independent pipelines anyway. You just have to shift them a bit or reposition them a bit. On, for instance, GPU-based systems, this is a lot harder to do, to process on a per subpixel basis because it's much harder to parallelize the entire algorithms there. So because of this crosstalk artifact, actually, in displays, there are 2 types of defects that come with that. So first of all, you have inaccurate colors, because if the electrical fields push away each other a bit, they will overlap with the blue, so it desaturates the yellow. So if you don't calibrate for an LCD-based display, and you look at the red primary, the green primary, then the yellow will be desaturated by nature because of this effect, the crosstalk effect. So, and the second thing is, of course, you have the wrong positioning of your information because of the crosstalk. So you also have an unpredictable sharpness, let's say, because the sharpness will vary depending on the subpixel base of your information. So by doing subpixel processing, you can actually solve all these problems. So that's why in our displays, we perform this type of circuitry. I don't need to explain the details here, but basically it means that we apply lookup table for each subpixel independently. And the way we implement this in our display is one of Barco's patented techniques. So let's talk a bit about the color gamut mapping and the challenges which come with color gamut mapping. So with high dynamic range signals, you define a, let's say, high dynamic range in luminosity range. Usually it also makes sense to combine that with a higher range of colors or a wider gamut. Now the problem is, and now we come back to the 2 important properties of the human eye. So that's why I spent some time on that briefly. There are 2 things you need to do. If you have an HDR signal, you need to convert it to the optical domain because the color mixing, the color processing you need to do, or the color gamut processing in order to map the source to a display, that must be done in some signal representing linear light. So that means you need to perform the electro-optical transfer function. And because it is very curved, you need more precision here than there. I will come back on this in the next slide. So then you can perform your color gamut mapping. And once that is done, you can return to whatever HDR standard it was encoded, whether that's hybrid log gamma or PQ or so. So the problem is here, if we look what do we need to perform these functionalities? If this is like a 10-bit input, all you need is really a 1K by 24 lookup table. That's easy to implement. But if you want to perform the inverse function, you have 60 million addresses in the lookup table, and that's not implementable for a random accessible lookup table. So this is a bit of problem. So basically, this means that it's a lot harder go back to an HDR signal than it is to convert from HDR to linear light. So when you have so-called high metric entropy, which means the average information in each bit here is a lot higher than the average information in there because you don't invent new information. So the average amount of information every individual bit here depends on the information in all other bits. That's basically the problem. Doing that and converting that to a linear domain where you have a lower entropy, it's very easy in general to do that for all kind of processing algorithms. But then going back to a higher metric and entropy again. This is a lot more difficult because obviously you cannot simply calculate the inverse. So you need, let's say, smarter things to do there. You need to think about how you can implement that. And this is illustrated in this slide here. This slide illustrates the electro-optical transfer functions for a couple of standards, like the Rec 709, sRGB, but you can see hybrid low gamma. And then you can see like Dolby PQ, it hardly moves. So the problem is, if this is your video input and this is the output of your electro-optical transfer function, you see that you need a huge precision to distinguish all the values here and obtain a new value there. So to preserve the details in the PQ signal, you need to increase your precision dramatically more than you would need to do them in, let's say, standard definition applications. And this is illustrated here. Actually, you can quite easily calculate that yourself. Just look up the electro-optical transfer function and put in this first value. You will see that you will need only 13 bits for a 10-bit input. You will need only 13 bits for Rec 709, 14 bits for sRGB. But it's quickly, it goes up for hybrid low gamma. That's already 20 bits equivalent linear precision you need. And for PQ, you need the equivalent precision of 24 bits. So this is the problem. There's a very steep curve here, which means that there's a lot higher, let's say, a lot more information in this coding than there's information in this type of coding. So one way to, let's say, approximate here higher precision for the optoelectrical transfer function is by simply perform some type of piecewise interpolation in between certain amount of anchor points. Problem with that is all known interpolation techniques between these anchor points tend to create, let's say, errors in colors that are not acceptable in many applications, especially not in color critical applications like, for instance, post-production, in broadcasts for grade 2, even grade 2 or grade 1 monitors, cinema-like conditions, and residential, but yeah, in a lot of the markets Barco is active in, this type of solution would not be acceptable. Better approach is to convert that huge precision you need, or the equivalent linear precision you need, to convert that to a type of arbitrary precision floating point. And this arbitrary precision floating point can use a lot fewer bits than the total input as illustrated here. So for those who know floating point, this is nothing new. Actually, a floating point value just uses a couple of bits as a mantissa, and it encodes this linear precision as an exponential value in combination with a mantissa. If you stack both values, the exponent on top of the bits of the mantissa, this is the function you get from a 20-bit input to a 10-bit floating point or arbitrary precision floating point value. So I've illustrated that here for, not very coincidentally, because it's a real use case. It's illustrated for hybrid low gamma, which is used a lot in, for instance, endoscopy cameras and so on. For hybrid low gamma, I've illustrated this with a 4-bit exponent. So that's an arbitrary number. That's why it's called arbitrary precision floating points. So it's almost as precise as a half float, which is more standard in software, but in hardware we can, in FPGA, we can use whatever we want because it's programmable. We can have like a 6-bit mantissa and a 4-bit exponent, for instance. So this example is not a coincidence because it's the best match for that given application. Now, the question is, how do you determine the best arbitrary precision processing for performing a function like this? Again, this is not a coincidence. The inspiration comes, the name of the technology we have developed comes from a beer after drinking a couple of them. By the way, I can highly recommend it. So we call it lossless undetectable perceptually uniform luminosity unit steps. I'm not going to explain this equation, don't be afraid, but it's the true one. It's, by the way, extract from the patent. So, you can look it up if you want. What we basically do, maybe first I need to explain that also in SDR signals, there are a lot of the transfer functions can be approximated very well by just a simple gamma function. And historically, even like in the end of the 90s, started in Barco early in the 90s. So by the end of the 90s, we were doing displays in flight simulations, for instance, and the use case there was for pilots to land, of course, at night. And they still need to see some detail in the very dark details of the landscape. But you need to, at the same time, be able to display the lights of an airport. And so there were no HDR standards at that moment, at least not usable ones. So people used like a gamma of 3, which is also a very steep function. And so if you think about it, sRGB is usually approximated with a gamma function of 2.2. Sorry about the European way of writing these numbers. So 2.2. In cinema conditions, where you have a more controlled ambient light environment, the gamma is approximately 2.6. And in flight simulators, for instance, people have been using for at least 25 years already gammatization levels of 3. So the higher the value of gamma, the more curved the function is. And so we have done it, we have made our own kind of perceptual matching as perceptual quantizer standards to perform our image processing very efficiently. Based on the observation, if you have a gamma function and you take into account the contrast of the display, so the darkest level the display has, then you keep this level constant. Now, if you increase the gamma, and if you continue to increase the gamma, then normalize this part. So you renormalize what's left of this function. You move that point here. Something interesting happens. So you have a more and more curved function, but you're using a smaller and smaller part of that more and more curved function. This is actually a limit transform. And what happens then is you start with an equation where the gamma is an exponent here and the video is the base here. And you end with an equation where the video is here. I'm not going to through all these steps, but it's important to notice this relation. It means that you can approximate the perception even in SDR, moving, let's say, seamlessly towards HDR. You can approximate these equations by quite simple exponential equations. Now, the question is really now how do you determine the best exponent and the best arbitrary precision parameters? Well, it's quite simple. You just plot all these exponential functions. These are the dotted lines. Now, look what happens with the arbitrary precision functions. So this is the 4-bit example I've shown earlier. So this is for a 1-bit exponent, which makes no sense, obviously. A 2-bit exponent. So suddenly the steepness increases by a factor of 2, then again by a factor of 2. This is what's happening with arbitrary precision floating point. Also with standard floating point notation. So you can see that the higher the exponent goes, the better this matches. Basically, you can derive from your environmental condition the entire contrast of your system. You can map that to the best exponential function. That exponential function can be mapped to the best exponent with you can use for your arbitrary precision floating point format. And this technique is what we use internally in our image processing pipelines. And we have, of course, patented this technique. Now, this looked like a very complex explanation, and I wanted to explain this with an analogy. Again, sorry, we're in West Flanders. So our inspiration and a lot of our wisdom actually comes from what we see around us. And we have an expression, it's easier to turn a pig into sausages than to create a pig from sausages. And it's actually true. And the analogy is, analogy works perfect because in this animal, every bit of the animal is a function. The value of every part in this animal is a function of everything around it, everything connected to it. In the sausages, it's no longer the case. All the pieces have like uniform value, and you have a much lower metric entropy. And now, if you would build a machine, it would be very hard to create a pig. No one has ever been successful with that so far, even in our region. So it's just so that you can remember why it's so difficult. So this step is indeed, everybody knows, oh yes, this is very difficult. So a last thing about color gamut mapping, the last slide about that is, we are near the end of the presentation. The last slide is on color gamut mapping is explaining the difference between white gamuts and extended gamuts. Many people don't realize that there are two ways to extend or to build a large or to represent a huge amount of colors. The obvious way to do that is, yeah, very naturally, you just put your primaries very far away from each other. And naturally, yeah, on the display technology, this is what you have to do. From a display side, you need to mix colors, and you can only have positive amounts of photons from each primary. So on a display, this is the only thing you can do to create a white color space. In video processing pipelines, or in encodings coming from a camera or other devices, in the transmission of video signals, you can also do something even more clever. You can simply extend the gamuts. You keep the primaries where they were for instance, Rec 709, a standard gamut, and you allow the coding for negative amounts of these primaries. So you can do extrapolations instead of allow that all the coefficients of the primaries are between 0 and 1. You can have maybe 1.2 times green minus 0.2 times red. That extends the color gamut. Big advantage of this is that you can preserve your standard gamut calibration. Maybe you have equipment that is tuned for standard gamut calibration. And in a lot of cases, you don't have to change production environments to calibrate displays. By extending the color gamut, you can use existing calibration and reuse basically the rest of your image processing pipeline. So the extended gamuts have basically the same gamuts as the standard gamuts. So examples, probably many of you know Rec 2020 and so on, Adobe RGB and so on. These are all white gamuts. If you look at extended gamut examples, we have Rec 1361, which is literally a type of extension of the Rec 709. Deep color, which is a bit of a variant, XPYCC, is also a different interpretation of a stretched version of the Rec 709. So by processing in extended gamut mode, sometimes there are benefits in some of the use cases. For instance, band calibration is critical in the standard gamut domain. And so the final topic, only 2 more slides, or 3. So it doesn't help to do a lot of processing with very high precision. Because a lot of the display technologies have, all display technologies obviously have finite precision. And many of them don't have enough precision. As I explained, the LED walls practically, they are pulse width modulated. DLP-based projectors also, they are pulse width modulated. These type of displays tend to have a precision of 13 to 14-bit linear. Many LCD panels in practice are driven by digital to analog converters of 8 or 10 bits even. So if you have a very precise image, this is not just, this is for the sake of the presentation. It's not an HDR image because I don't think PowerPoint can handle it decently. So this is a standard image. It's just explaining what dithering is doing. If you start from this image, then you reduce the color palette. What you obtain is a loss of detail in certain regions, of course. So if you throw away some of the bits, if this would be, if this is standard HDR and this is a set of web safe colors, you're reducing the amount of colors which the display can handle. By the way, this reduction is very similar in amount to what's happening if you reduce HDR to a practical display. Most practical displays or high-end displays, of course, they can handle more colors than web colors, web safe colors. But you also start from a more demanding source like Rec 2020 with a lot more detail inside. And so actually these two, if you look from a distance, these look very different. Some of you might be surprised that these two images actually have the same amount of colors. The only difference is that this image is using a modulated version of these colors. So if you look from very close, you will see all pixels have one of the colors that are also in this image. So basically, dithering techniques I referred to earlier tend to create a perceptually correct average in, let's say, an area as small as possible. And in displays with moving image data, you can also take average out in time. So a good dithering algorithm should create the correct average in an area as small as possible in a time as short as possible. That's what a good dithering algorithm should be doing. The example here is using a basic so-called Floyd-Steinberg algorithm, which is basically using a form of error diffusion. You can just Google this, or it's on Wikipedia, you can find what it is doing. Basically, error diffusion just runs the color, distributes the errors across the neighbors, and does that again and again for the neighboring pixels iteratively. So these are examples. Unfortunately, some of the modulation is lost in the translation to PowerPoint. But this is our dithering algorithms compared to what is applied in most standard engines that perform so-called pattern-based dithering techniques. So pattern-based dithering techniques are very predictable. That's why they are very popular. But they tend to create interferences. And actually, the point is proven here because PowerPoint interferes with it and gets rid of the patterns, and it creates bending again. If you would start from the real picture, you would see clear patterns, and you don't see them here. Because this is a stochastic distribution of exactly the same color palette. But this one is based on the same type of modulation that is actually in our human eye. So we all know the examples of, let's say, if you have a brick wall and you point a camera at a brick wall from a certain distance, you will start to see interferences. You will see all the weird parabolic and hyperbolic interferences and so on. So-called moiré artifacts. We all know this can happen. We don't have that with our human eye. So to try it from multiple distances, stare at a brick wall, you'll never see any kind of money. Why is that? That's because we have our retinal cells in our eyes are distributed in a so-called Poisson disk distribution. And this is driven by millions of years of surviving. And this distribution doesn't cause aliasing. So if there's like a dangerous tiger somewhere in the corner of our eye, we see the right thing with this stochastic spreading. If we would have other arrangements, this could have happened, but probably they all died. So this really gives our eyes an advantage because it cannot interfere with that. So, and just to illustrate, this is the final slide. What is going on with this kind of scheme? So a Poisson disk distribution. This is the two-dimensional spectrum, and this is representing the energy of our modulation technique. So this is the true extract. Actually, this figure is also extracted from the patent application. You will see there is not a lot of energy in the very low two-dimensional frequencies, and there all the energy is outside there, almost like blue noise. So we put all the energy, the modulation energy, outside there. This is almost uniform distribution because it's almost a uniform distribution in this area outside the circle. So the Poisson disk is intended, of course, to avoid graininess of the modulation techniques. So you don't want low frequencies in there because they would be visible, but you want this to be as uniform as possible. If it's like a uniform spectrum, it cannot interfere. The only reason why interferences occur is because you have peaked spectrum, and that's what a lot of other modulation techniques do. They introduce a pattern which is repetitive, so you have spectral peaks. With our modulation technique, we are not doing that. We are not the only one on this planet doing this kind of techniques, but we believe we have a technique which can go a bit further. And with our solution, we can literally dither about 10 bits on an LED wall, which turns a 14-bit LED wall into 24 bits, even viewed from quite a close distance. So we use that, for instance, in our control rooms and in high-end residential. So that's, I think, the final slide. So it is important to perform a form of dithering. Yeah, maybe one last word about the schematics of this. Technique is actually very, very cheap to implement. All you need is just, you need to count columns and lines, where there's a lookup table, you generate noise, well, intelligence noise, you add that to the video, and then you truncate. That's the circuit. It cannot be more simple. So, and this technique, dithering in general, is really required to preserve the precision of HDR signals when feeding a display. So, if there are any questions, I would be glad to answer. Yeah.
Well, key takeaway, so arbitrary precision floating point for a 3D lookup table. So each point within that 3D lookup table is an arbitrary, it is one of those implicit exponent floating point numbers within that cube. Is that correct?
Yeah, there are two. If you implement a lookup table, there are two things you need to do. So you need to address the lookup table, and you need to somehow represent the data in there. So using arbitrary precision at the, but it's a good question because I did not pronounce that very well. I did not emphasize that indeed you have these two aspects. So if you apply arbitrary precision floating point to the addressing, what you're actually doing is you're redistributing all the different anchor points in your lookup table in a, let's say, in a way that it better reflects the perception of the human eye. If you move from linear encoding to arbitrary precision, you're putting more precision or more anchor points in the dark tones and fewer in the bright levels. On the other hand, you have the data encoding, and this also makes sense to represent in a floating point format, because if you're processing data with this kind of representation, and I did not mention that, if you calculate in an exponential format, in image processing, you need to do a lot of stuff like multiplications and treating the color gamuts. This is a combination, in many cases, it's a combination of a lot of multiplications. If you deal with exponential encoding, approximated by this arbitrary precision floating point, the multiplications turn into additions. So instead of multiplying, you just need to sum. And this saves a lot of resources. It makes it a lot more efficient. So very good question. So there are the two aspects, and they are both quite important. One is important, so the floating point, arbitrary precision floating point addressing. It's important to spread the anchor points in the lookup table to match, let's say, the use case in the best way. And using arbitrary precision floating point for the data, the video data itself, can save you a lot of cost. It doesn't make it more implementable, but it saves, let's say, processing power as well. So it's not the last aspect is also applicable in software environments. So it's not just an FPGA thing. The first thing is more like an FPGA thing. Good question.
Then example one with the laser projector, had a question about that one.
Okay. Let's turn on the slide and yeah, go on.
Okay, so the phase distribution, the phase mixing technique there. So for that example there with the sun with the rocks, that whole image, that frame is going to have an average pixel level of some value.
Yeah.
Is the laser itself being modulated from one frame to the next with a total optical output to match that? Or what's happening to the extra energy? Where does it go?
Yeah, good question also. So you can indeed modulate a laser, but you cannot modulate it in real time. So what is you can indeed modulate the laser per scene and apply slower dynamics, almost like HDR 10 plus formats and so on are doing. That would be like a global dimming. Actually, global dimming is also implemented in standard projection systems. So it's not only implemented in this type of engine. So in this type of image, you really take care of a certain light budget, and you always distribute that light budget with a phase modulator. You cannot, the phase modulator cannot send light away from the screen. We don't do that. And there's quite a good reason for that, because it's a huge amount of light. If you would say, oh, let's just send it in an absorber or something, because the light should disappear, then you cannot make like 65K lumen just disappear. That's, you can literally burn something with that. So actually, when this technology was developed, I'm telling you a little secret. If we were developing this technology and projecting on our nice, in our very nice building, you just saw, we had nice and new painted white walls, and we were projecting on that. With the little accidents in the algorithm, we were steering the light sometimes a bit too fanatically, and indeed we could burn holes in the walls, and quite deep. So it's, of course, by now,
Genius.
I don't want to scare you. Please buy this technology. It's very good. It's reliable. But just to illustrate your question, we cannot just remove the light and send it to some absorber, because there is no feasible device to do that. We cannot do that. Yeah. So the phase modulator itself always just redistributes a budget of light. And in this case, indeed, it will send a lot of light there. and just use enough light for the rest of the image.
Strobe lights are challenging.
Yeah, so the challenging stuff is, of course, in handling the balance and knowing where to send the light, and also steering this phase modulator itself. So calculating the image on the phase modulator is quite, let's say, difficult mathematics. We call it computational optics. I don't know if everyone on the planet would call it like that, but in Barco, we like to call things our way. Yeah, good questions. Thank you.
Yeah, you mentioned a few ways of doing the HDR and HDR conversion
Yeah.
using FPGAs, 1D LUT, 3D LUTs with different interpolation. Maybe I missed it, but did you talk about implementing it just as a math pipeline in an FPGA with polynomial approximations?
Yeah, I do believe I mentioned it, but maybe too shortly. Indeed, you can do mathematical formulas like, you know, if you would just take a square root of a signal, you would have some type of a roll-off function or just a gamma. You can implement it, so you can use DSP. The problem is that in most cases where you need applications like tone mapping, you also need to compensate for perceptual errors, and so that makes the functions a lot more complicated. Just look up, for instance, DICOM. DICOM is even a very simple principle. That formula is like a 10th order equation. The numerator is like a 10th order equation. The denominator is also a 9th order equation, I believe. Then you need to take the logarithms of that and so on. So it's mathematically, it's computationally very intensive if you want to do that. And even that does not always work. So in order to keep it generic, to keep it tunable, I think most practical tone mapping algorithms rely on lookup tables. But indeed, it's perfectly feasible in some cases to just use some DSP for that. It's a function called UDA. So you could use a part of a sine wave if you want, if you would have an efficient acceleration for that. That could be feasible as well. But in practical systems, you don't see that often.
Usually in FPGAs, you run out of memory pretty quick, especially with 3D lookup tables when they're 33 by 33.
Yeah, that's correct. Yeah.
I've seen some broadcast products that do the math pipeline, and I wasn't sure if you're implying that maybe they're not quite as good as a 3D LUT, or do they have to have 10th order operations approximations to be as good as a 3D LUT?
I know there are, I think I mentioned that there are other ways to implement this, but I just wanted to give a couple of examples. And the reason why we tend to use in our systems a lot of this functionality based on there's some mismatch of human perception versus colorimetry. And the second aspect is the defects of the display itself. You also need to tend to compensate for them, like the defects I described about crosstalk, for instance. Those already bend the color space dramatically. And so you not only want to perform the tone mapping in that functionality, but also within the same functionality, you also compensate for the defects of the display. And that's making, you know, a lot more extreme mathematics, I would say. Especially if some of those steps are based on pure calibration. If you just calibrate a number of points and you do curve fitting through that, mathematically it becomes a lot more, I would say, advanced in you know, the balance. If your FPGA is filled already with block RAM and you still have a bunch of DSP, of course you can do it like that. So it's a good remark, but in our company we are not using it that way, and I haven't seen it unless it only deals with standards without the calibration correction.
Yes, I think that's the case.
Yeah.
It's just 709 2020.
Yeah, indeed. Then you can do that. Yeah, of course. Yeah. Yeah, you can. If you dive into the recommendations of the video standards, you will often see a variety of different flavors of implementation, either 1D or 3D LUT based, or indeed a full pipeline. And I did not mention that because it's quite complicated, but you can also apply a one-dimensional LUT on the Luma signal, or on ICTCP, only the I signal. You can apply a one-dimensional lookup table on luminosity and then compensate for the color defects you're introducing. And you can find this kind of recommendations also in the standards. If you read about road mapping 21, 2100 and so on, you can see these pipelines there. So indeed, you can implement it as a pipeline, but it's very hard to combine it with other aspects of calibration and the perceptual versus colorimetric mismatch, which is ambient light dependent also. Yeah. Thank you.
So most of the products you mentioned here were like focused on like live applications, right? Like surgical theater,
Yeah.
live events, flight simulators or whatever. For predetermined content on a predetermined display, can you pre-render this and calculate the things exactly with those 9th and 10th order equations and deliver it in that format? And does Barco make any such products, or are you focused on the live aspect of that?
That's more than just one question. First aspect, so can you do it? Can you just pre-compute that if it's a recorded movie? Of course you can do that. That's what color graders are doing actually. You could have even some AI engine processing an image, say, tell it, this is how I want it to be remastered, modify a couple of scenes, and AI algorithms can do the rest. And they will calculate like half a minute per image in some cases. And if you render a movie and you wait for like a week, you get indeed a perfect result. So yes, it's definitely pre-computable. It does not always have to be done in real time. But even in markets like high-end residential applications, it is not done. You would expect there, you would see this kind of implementations, but I haven't seen it. Maybe they existed, but I'm not aware of it. I'm only aware of a number of companies, including ourselves, that make algorithms that can, in real time, remaster a certain movie to, let's say, a new standard for high-end residential. And the reason for that is, well, one of the reasons I was told is that in the high-end residential market, for instance, when a movie is launched, they want to have it instantaneously. So the movie is released as for a, let's say, an ideal production system for cinemas. Then you want to see the same content in a very different environment or a very different display technology. And they want to see it the first minute. That's what they pay for in this kind of application. So in the high-end residential market, quite rich people, usually they have a lot of oil and so on. So we have a lot of setups in high-end residential in Dubai and so on, I can tell you. And Abu Dhabi, it's one of our biggest markets. So these people, they want to see the movie when it pops up, and there's no time to spend like, yeah, even a few hours or so. They don't do that. So there are companies that only do this kind of stuff, like MedVR, for instance. They have products. They make a box that does in reality nothing else than kind of real-time remastering, analyzing scene per scene with very little delay, only like a couple of frames of delay, and they process the movie in real time. Our algorithms do the same, built in the display. But this is the other part of the answer. So yes, you can do that, but I don't see there is probably software there, but some markets don't ask for that. So, but indeed, you can pre-compute it. You can. You also have to be aware that, for instance, if we will launch this technology later on, this technology will target the cinema. I know it's getting. Yeah, no problem, no problem. If we target the cinema markets, this will be the high-end version. We will obviously create a portfolio with, let's say, a number of grades of image quality with this type of technology. Obviously, we don't want color graders to remaster their content for every type of display system or technology that we create. Also there, we are going to perform this remapping in real time. Because also during post-production, they really want to see the result on different display technologies. If I've seen some color grading companies from inside, and they are really looking at different screens, sometimes in parallel. What are the different results on OLED, LED walls, projection, and so on. So this is also a good reason to, in real time, manipulate things and really see what's going on when the tone mapping inside that display is real time remapping. So you can, of course, do everything in software and recompute all contents. I'm quite sure that you refer to as perform the ideal mathematics. In some cases, it will indeed be better. So it's clear that we, because of, I think I stressed it a couple of times, the challenge is to do all this in near zero latency. And this, for sure, this limits what you can do. So you need to make a couple of compromises because it's real time. So for sure, you can, in cases where it's possible, you could indeed pre-compute the tone mapping. Yeah. Good remark. Everybody is tired. Oh.
Thinking, wondering how Parco's work in this area applies to more commercial applications, such as, going back to my background in video, the push has been to get rid of all film that you watch, and we watch it in video. Every movie theater now is all video. But there's still a problem in getting the maximum resolution, well, at SD or HDR, whatever you want to call it, getting the maximum resolution that a person can visualize in a typical movie theater. The type of large screen TVs you buy, people leave the lights on, so you can't visualize that. But if you want to get the maximum picture, I've found that somehow you got to stretch those blacks. Wait a minute. So it has occurred to me that, son of a gun, if there's a way, or if somebody is working on noise reduction that is programmable to the low end of the spectrum, stretching of blacks, is that anything that gets looked into as far as the deeper mathematics of what you're doing with the colors and high end and so forth, customized noise reduction to make the picture look better, like you show with that little picture of the cabin and trying to bring out the blacks, but it gets noisy.
Yeah, so a good remark about the noise reduction, because indeed, if you would apply in many applications, slightest graininess in a natural image tends to result in some unnatural defects if you, let's say, overcompensate the dynamic range tone mapping. So what I didn't mention, because the presentation was long enough and I could have added 1,000 more slides. But what I didn't mention is that if you apply 3D LUTs, don't always have to process every single pixel by itself. I mentioned subpixels, but you can go, you can also go the other way. And what a lot of techniques implement is you characterize the spectral bands that are indeed defining the perception of noise and the perception of graininess in the image. And you leave those spectral bands untouched. So to come back to your remark, basically you can perform multi-band processing. So you have a traditional video signal, you split that in multiple frequency bands. There are several techniques to do that. And you can then apply the tone mapping functionalities like a 3D LUT on each of the bands separately. And in many applications we have seen, you can better just leave the high frequencies untouched. And so this comes back to your remark. If you have like, for instance, Dolby PQ contents where you have small textures in bright highlights, why not split the signal in two bands, leave the high frequencies like that, then transform all the lower frequency contents and then reinsert these high frequencies untouched. It is perceptually encoded anyway. So if you just reinsert those frequencies, you will see them, you will perceive them the same as they were before. So you're not compressing the textures and the details, and you're also not overly stressing the graininess and the noise in dark tones, for instance. So multi-band processing is one of the solutions to tackle that problem. And it can also simulate, let's say, a more classic look and feel of film material. You can even emulate the graininess. Again, this comes a bit back to my last couple of slides about the Poisson disk distribution. You can also use this kind of techniques even to isolate frequency bands two-dimensionally and then apply certain emphasis on these bands. And in our tone mapping algorithms, we use techniques which are based on classic Laplacian pyramids, if you are a bit familiar with the terminology. So you can basically downscale an image by a factor of 2. Let's say you start from a 4K or an 8K image, you can reduce it by a factor of 2, and again by a factor of 2, and again by a factor of 2. So you can apply multiple progressions to that. And then apply your tone mapping to the lowest resolution, then reinsert the difference in the frequencies, apply some correction to that, then reinsert again, and so on. So these are called Laplacian pyramids. You can Google it if you want. And these techniques are indeed creating a better match with what you described as the analog feel on film. This is indeed the more complicated stuff I did not explain about, but these are standardized techniques. So they are used a lot, and they are also popular because not only because they match better the perception, but also interesting is if you reduce the resolution of an image and then you perform tone mapping on that lower resolution, you're even saving resources. So that's an extra benefit you get. So you can subsample. So in some of our processing algorithms, we do that using wave-flat transforms and so on. But it would lead us too far here to go into detail. But indeed, your remark is totally valid.
In a sense, it's perceptual tone mapping.
Yeah, well, one of the aspects of perception I did not describe is this multi-scale. So one problem you can easily imagine if you don't process in a scale invariant format is that let's say you perform tone mapping on an 8K resolution source. And then you, for instance, apply resizing and you show it on a 2K display, for instance. That result will be very different from first resizing the 8K to 2K and then applying the tone mapping per pixel. You don't want that in many cases. especially for instance, in medical use cases where you have a variety of displays, one where the surgeon is looking in real time, one is a big display hanging on the wall. Another display might be a remote participant, maybe a doctor providing assistance from another hospital and so on. So you have to deal with a mixture of different resolution displays, but you want to perform tone mapping in a way that it is independent of the resolution. And so taking out these high frequencies of the signal also helps to make the tone mapping appear more resolution independent. So this it's almost like in analog film. It's not going to change a lot if but the perception of analog film does not change a lot if you have a film with a little bit higher ISO. You have a bit more noise. You have a bit larger particles, but the overall look and feel stays the same. With tone mapping, if you would apply that per pixel on very high resolution, you get a very different result than if you first resize, then perform that tone mapping. So you need to take care about where to use, in which phase of your processing pipeline you are applying the tone mapping, because the place in your entire pipeline from camera to display will also determine what the result is, also perceptually. So if you really want to avoid that, the best solution is to perform multi-band scaling, like wavelet transformers or Laplacian pyramids and so. But this was a bit outside the scope of this presentation.
Thank you very much, Ron.
Okay, thank you.